Okay, good morning, and well, thank you again. We've had the predicted amount of delays as far as starting is concerned, but I am actually very happy to be here at the NBRC and to talk a little about some issues which may be of interest to a wider community. Okay, so the title of my talk is, as has already been announced, Multistability, Attractors, and Chance. And in trying to give an idea of what this kind of topic is and why should neuroscientists be interested in it, here's an image on the right-hand side of the screen of the famous Necker cube, which I'm sure is more familiar to all of you, and you all know more about it than I do, except that this is always trotted out as an example of multistability, or at least bistability, whenever dynamical systems people talk about it. As is well known about the Necker cube, some people will see the cube is oriented upwards, that it is coming out of the screen in one way. On the left-hand side, you will see the cube is oriented in one particular way, and on the right-hand side, you can see some people will see it like it is shown on the right-hand side, the cube going backwards. Now, yeah, it's just that I'm not able to immediately know how to shut. Yes, I'm sorry, I've managed to do that. Okay, so some people will see the cube face, the cube oriented downwards, and some of you will see it upwards. And this is a famous illusion, if you like, that is shown in so many of your neuroscience discussions. But what this will also help to sort of put some of the notation of what I want to talk about today. People will see it one way or the other, and these two distinct final states are what people call attractors. Now, which of the attractors any individual sees depends on initial conditions. And as is also well known about this optical illusion, some people will see this cube switch orientation from one side to the other. You'll start out seeing the cube, this particular cube, because this doesn't have the dotted lines in it. Some will start out seeing this cube coming out, and then they will see it going, coming out to the right, or then going out to the left, etc. And you'll see the switch between these two distinct final states, which are the two attractors. So bistability, this is an example of bistability, is something that we actually know a lot in visual neuroscience. The third word in my title was on chance, and chance, in a way of thinking about it, is central to this discussion. How does one see it coming out or going in is, quote unquote, a matter of chance. And that chance depends on the fact that you have two attractors. But the way in which we use the word chance is that chance is the absence of necessity. If something happens without it having to happen, right, then there is a question of chance. We know that if I were to take an object with some mass and drop it, there is no possibility that this is going to go upwards, because it has to come down, and there is no chance in the kind of motion that it will follow. There's a subtle difference between what we understand as chance and what is generally termed contingency. Contingency is a future event, something that is going to happen, that is possible but may not be predicted with certainty. So there are many contingent events. There could be an earthquake in the next 10 minutes. Definitely possible, given the fact that we are sitting in Delhi and Gurgaon and Manesar. There could be, there may not be a thunderstorm, but it's very likely that it could rain tomorrow. So these are all future events that could happen but cannot be predicted. Now, chance is the fact of something happening without having to happen. And there's a difference between these things. And the reason I bring it up is that many times when we are dealing with the microscopic origins of certain phenomena, we have to worry about the possibility that things are governed by chance. Now, chance itself, we know, plays a role in a lot of situations, and particularly to do with our natural world. Jacques Monod, who got the Nobel Prize, I don't know, some 40, 50 years ago, talked very importantly about chance. And he says that nature relies on chance and not on destiny. We do realize, when you know more about molecular biology and genomics and so on, that it is a brilliant accident of fate that we are here to talk about things, because we are just one end of a branch of evolution. Every branch was created by chance mutations, right? A great statistician, C.R. Rao, has pointed out that if something is governed by chance, you may not be able to make a law out of it, because for laws we need simple rules. I'm going to come to that later. But maybe there are laws that govern chance itself, and that's one of the purposes of today's talk. Now, we use ideas of chance all the time in everyday world. For example, if you want to choose between two outcomes, you say, let's toss a coin. Who's going to go first in batting or whatever, you toss a coin. And this we use all the time in games of in sports, all right? Now, the reason why we seem to rely on this is that we feel that, the coin has two faces, heads and tails. Whether it's going to come up heads or tails is just a complete set of chance. So you allow somebody to toss it, and somebody calls out heads, or if it comes up heads, then they get their choice. But if you think about the physics of a coin toss, there's nothing random about it. If you take a disk of a certain diameter and a certain mass, and you send it with a velocity u upwards, gravity is acting in the downward direction. Give it an initial angular momentum, right? And once you do that, then, on the right-hand side of the screen, you should be able to see some very simple equations which were written down essentially by Newton or Galileo or someone like that, which tells you that the coin is going to have its height. Y is the height. And it says that the acceleration is just due to gravity and nothing else. If it starts out at a distance a from the from above the ground and with a velocity u, then it will spin depending on the angle theta. And okay, so it's just some mathematics which can be done. And this was done by Keller in 1986. And he pointed out that when the coin hits the ground, let's just assume that it hits the ground at time t0, when the height is equal to 0. And when it hits the ground, it hits at a particular angle. So whether it's going to be heads or tails is going to depend on which angle it made with the ground. That angle is going to depend on the initial velocity and the angular velocity. So you do the analysis, or even simpler, you go and read Keller's beautiful little paper. And the analysis is straightforward. And what he shows is that if you plot the as this angle as a function of the initial velocity and the initial angular velocity. The initial velocity is u, and you scale it out with g on the, for convenience. And on the y-axis, you've got the initial angular velocity. All right. Then, if your if the angle theta comes in the black region, you will get you'll find that it comes up heads. If it's in the white region, you come up tails. So this entire space of initial conditions, right, is just broken up into little strips of black and white regions like a zebra pattern. And if your velocity is so, and your angular velocity is of a particular value, then you can predict exactly whether it is heads or tails. Now, this analysis was done for a infinitely thin disk, and what you can do a lot of nice mathematics. And basically, what Keller showed is that look, I can get any probability of heads and tails to come up depending on how I choose my initial velocities. Right? Now, this sort of the theory was redone by Madhavan and Young in 2011, taking not an infinitely thin coin, but a coin with a certain thickness. And the analysis is very, very similar. All right. This is, just a little more sophisticated. And then what they showed was basically that Keller's analysis was perfectly correct. And as you increase the velocity u, and you increase the angular momentum omega, initial angular momentum omega, then if I take any set of initial conditions, sufficiently far, very high velocity and very high spin, then I get approximately equal amounts of heads and tails. All right. So what you can see over here on the, unfortunately, I'm not able to make my cursor move around. But nevertheless, I hope you can follow what I'm saying. In panel A, you'll see that the blue regions are, let's say, tails. The red regions are heads, right? And if I take my group of initial conditions very, very close to the origin, then I know that I'm mostly going to get heads. If I start with heads, give very low velocity and no spin, then the disk almost just goes up and down and just comes back, all right? Now, on the other hand, if I give it a huge velocity and I let it spin tremendously, then I go to the set of initial conditions way up at the other end of this square. And there I can see I have roughly equal numbers of heads or tails regions, right? Now, there's a lot of analysis that you can do, and you can follow this rather nice article. It's a short 2-page article in Physics Today, but it's an experiment that you can do. And so somebody did that. Actually, this experiment predates this paper, where this group looked at a mechanical coin tosser, and they could adjust the velocity and the angular momentum. And with the careful adjustment, they said, the coin started, when you start it with the heads up, it will toss up and come back and land up heads 100% of the time, right? Namely, if I can always adjust it so that I can give the precise velocity and the precise angular momentum to always land in a black region, right? So this is an experiment that one can do, all right? And the conclusion was that coin tossing is physics, okay? It's something which is very simple in physics, and it's not random, all right? Now, I'm going to request, okay, I just thought that I will take a break for a moment and ask how things are going. Well, where am I? Arpan?
It's perfect. I think its sounds are also okay. No problem at all.
The sound is okay and things are all right.
Yes, yes. No questions yet.
Okay, no, not a question. I mean, one of the problems of these wretched webinars is that somebody keeps talking and talking, and it's
No, I'm going back and forth between the GoToMeeting and YouTube, so it's okay.
Okay, all right. Okay.
Yeah.
So, all right. So now that I've just had a little break, I just want to point out that these ideas of chance are very important in biology, and the NBRC's, I mean, you all are at the interface of biology with a whole lot of other disciplines, and so one has to always worry a little about things like like noise, uncertainty, chance, and so on and so forth. Okay. Now, in biology, where all does chance play a role? The origin of life, to the best of our knowledge, life occurred once, or successfully once, on this planet, which is a very, very, very improbable event. All of natural selection, we know that there is nothing that is directing natural selection other than the interaction of an organism with its environment. And as the environment keeps changing, we know that different species come and go. And in particular, we made a transition, a billion years or more ago, from a single cell life form to a multicellular life form. And that also seems to have happened only once. And of course, very famously, we know that, these multicellular organisms grew and grew and grew, and, the dinosaurs evolved, etc., until one fine day, a meteor goes and crashes into the Yucatan. And that was also, best as we can tell, fairly random, happened only once, highly unlikely, etc., etc. But these have all conspired to eventually, as it were, allow me to talk to you today. But as C.R. Rao pointed out, we like to rely on simple laws. Laws that are beautiful, laws that are elegant, and laws that are certain. That is, they are not dependent on chance. And from the beginning of our civilization, we've been worrying about how to describe the world around us. So, among our ancestors, Kepler. Kepler made all these wonderful laws of, that the planets are going around in ellipses, simple curves, but that was a law, and that was very useful. Then eventually it led to calculus of Leibniz. Newton discovered the gravitational law and classical mechanics and so on. So increasingly we have looked for very deep principles as symmetries, conservation, always guided by beauty, elegance, and determinism. But the world is a messy place, and it's very difficult to assume that everything is always very pretty and everything is going to be very beautiful, especially when we know that stuff happens. So one can ask, what is the true nature of the world around us, right? Or if you want to put it in a little more formal language, which is the most appropriate mathematical framework so that you can properly describe nature. Now, we've worried about it as a species. We worried about it for a long time because we need to know and we need to understand how this is, how we are able to cope with the world around us. And in a sense, the trial and tribulation that all of us have faced over the last year, right, has been, the frustration has been that we are not able to control this problem as we think we should be able to. and good consequences that we realize that we can't control very much, and that's also all right. But still, what is the best way of describing the world around us? And as Einstein put it, Einstein pointed out to us that our descriptions of nature are only approximate most often. So he said that as far as the laws of mathematics refer to reality, they're not certain. And as far as that they are certain, they do not refer to reality. So the simpler, elegant descriptions that we are so hung up on may not be very, very accurate. And and as I've already alluded to it, frequently we are not able to predict what's going on because we don't actually understand the laws that are underlying them. Why should I, for example, start out by seeing the Necker cube coming one way out of the screen, and then suddenly I find it switching, to the other side? Why is it happening, and why does the switch happen at unpredictable times? A general catch-all answer for this is that they're all examples of nonlinear phenomena. And very briefly, there are natural phenomena that we describe very nicely, thanks to these lovely laws of Newton, etc., etc. And these are phenomena such as eclipses or sunrise times and sunset times, etc., which are very well known. You can go to the newspaper and figure out when is the sun rising or setting to within a few seconds. Also for an eclipse, and this is a personal story over here. In 2009, there was a famous eclipse in India that passed very close to us over here. And the whole point of this eclipse was that it was going to be it is the longest one until 2132. So for another 100 plus years, 112 years, you will not have such a long eclipse. But the data about this eclipse was already known decades before. And in the year 2000 or so, I learned about this phenomenon. And, all sorts of details could be found. It would be visible in many cities such as Surat, Varanasi, Patna, etc., etc. And it was on the 21st, 22nd of July, 2009. Now, the moment you see that it's in July, you say, I'm not going to go to Surat because there's a monsoon over there. But all this information is available many years in advance. And the path of the eclipse was known precisely. And it helped me to plan my trip, which I did. And I decided that, of all these cities on this path, I got my arrow back. All right, that I would go to Varanasi because it was almost on the line of centrality, and I was going to be able to watch this eclipse rather nicely. Anyway, landed up in Varanasi that day, and there were clouds in the sky covering the sun. I could see that there was an eclipse going on, and as the moon was covering the sun, and the clouds were covering the moon, covering the sun, and so on. But at the last minute, the gust of wind blew all of it out, and I was able to see the eclipse. But with all this level of prediction and planning, 10 years or 12 years in advance, I was still not able to talk about the weather on that day. So we are surrounded by phenomena, some of which are beautifully predictable and some of which are not. And it turns out that the weather is a prime example of a system which is governed by nonlinearity. And nonlinearity is important because it's everywhere. And many physical laws can be approximately made linear in a small regime of validity. And the advantage of linear systems is that you can analyze them completely and so on. But, it gives rise to simple and nice laws, but on the other hand, the real world is not necessarily going to respect that, because the real world has its own behavior. Many of you would have done this experiment in high school, where you have to measure the restoring force on a spring. How long does a spring stretch out, and the force is proportional to the distance to the extension. Now, this is a law which is a linear law, only true in a small regime. You can't pull the spring out. I mean, if you just pull the spring until it broke, there is no restoration. The spring will break. And the law is also broken. So, the point is this: if you want a very simple, linear, pretty looking law, you are going to be extremely restricted in the regime where it applies. If you take a simple pendulum, for example, again, this is an example that all of us look at in school even, and you can do the mathematics very nicely, and it's all straightforward. But the point is that if I take the pendulum and allow it to swing, let's say it starts at this particular point and I let it go, or I start it ever so closely and let it go, then the difference between one solution, okay, so here are these two solutions that I'm writing down as x of t and x prime of t, or x dash of t, and they differ only in small initial position over here, right? A small change in the initial position. The difference between x and x prime, you can work it out very straightforwardly. It's just some simple mathematics over here. If this difference b minus b prime is small, then this entire quantity is very close to 0, which means that x minus x prime will also remain very small. All right? And this is a very characteristic behavior of linear systems, unlike what happens in the nonlinear world. Now, about 50 or more years ago, in trying to study the weather, and in relationship to the weather, it was the study of the flow of air in the upper atmosphere. A meteorologist named Lorentz was studying the following set of differential equations. The dot over here represents d by dt. So dx by dt was this quantity, dy by dt is this, and dz by dt is this. And you can notice that it's an almost linear system, except for this term over here and this term over here, which makes the system nonlinear. And Lorentz found that when he did these calculations using a computer, on 2 different days, the calculations did not agree. And he traced this to the fact that the difference in the initial conditions was only 0 up till 4-digit accuracy. So let me just go back over here. If you take a simple pendulum, if the difference in initial conditions, x minus x prime, if that is, over here, the change in b and b prime is very, very small. It's 10 to the minus 4 or less than 10 to the minus 4. Then you've got sine of 10 to the minus 4, which is approximately 0. And that will keep x minus x prime very, very close to 0. So what Lorentz did was, he said that, how can it make much of a difference? And when he did the calculation on 2 different days, what he observed was the following. Starting at this point with very, very small change in the initial condition led to huge changes as time went on. So starting over here with 2 initial conditions, one of which is colored red and one of which is colored blue. If you start at this point, after a while, the red and the blue separate from one another, And after a certain amount of time, I don't know, call it 10 or something like that, you started over here with blue and you end up over here at the blue end. You start over here with red and you end up over here with red end. So very, very far apart. And this is something which Lorenz called sensitivity to initial conditions. And it's actually something which is very rampant. We see it all the time in our lives, and it can be illustrated in the following way. So the idea is that if a system is nonlinear, it can show sensitivity to initial conditions. And the result of that is that small changes initially can lead to very big changes later on. This sensitivity to initial condition happens in a simple equation. If I take a number x multiplied by 2 and throw away any part which is bigger than 1, then this is it's a way of just playing around with numbers. So if I start with 1/3, I double it, it's 2/3. I double 2/3, I get 4/3. But then I throw away the part which is bigger, throw away 1. So 4/3 minus 1 gives me 1/3, which I double is 2/3. I double that is 4/3, which is again 1/3. So if I start with 1/3, I'll just go 1/3, 2/3, 1/3, 2/3, etc., etc. Instead of 1/3, I can take an approximation which is good to a part, 3 parts in 1,000. We know that 1/3 is 0.33333 all the way to infinity, right? So if I just take 0.33, then I double it, I get 0.66. I double that, I get 1.32, but I throw away 1. So I get 0.32. Double that, I get 0.64. Double that is 1.28, throw away 1, so it's 0.28. 0.56. Double that is 1.12, I get 0.12. So what's the error between the true orbit and the approximate orbit? In the first part, the error was just 3 parts in 1,000. After one step, it was 6 parts in 1,000. After that, it was 1 part in 100. Then it was 2 in 100, 5 in 100, and suddenly it was 1 part in 10. Then the thing was 2 parts in 10. And you can see where this is going. Pretty soon, the error is going to be 1. Right? So you're going to be absolutely nowhere that you cannot make any kind of prediction because the differences, these small differences, grow so rapidly you can't predict. This is what we call chaos. And yet, if I start with one initial condition, I will go to the same object over here. If I start with another initial condition, I also go to the same object over here. That's because this thing that you see, the solution of the Lorenz equations is an attractor. So no matter where I start, I will go to the attractor. But on the attractor, my motion shows sensitivity to initial condition or chaos. So you get, and these are what are called strange attractors. If I just schematically show that I have attractor A, attractor B, attractor C, etc., one set of initial conditions might go to attractor A, another set will go from somewhere else also to attractor A. Initial condition may go to attractor B or to C or to D and so on. Okay? So it's very important not only to know what are the attractors of the system, because many attractors can coexist. And when many attractors coexist, we talk about multistability. If these attractors are stable attractors, then the existence of 2 or more mutually exclusive, that is distinct, stable, attracting states, this is called multistability. Bistability over here, there are 2 stable attractors, and this is very important in a variety of situations where you want to implement logic gates and so on, because all of logic and all of computation is built on 0, 1. So if you've got 2 states, you've got the possibility of computation. Here again, you've got two states coming in, going out. So this is also an example of bistability. Of course, you can have multistability. In the Lorentz system, for example, you have this chaotic attractor, but at the absolute center of these eyes of the butterfly, or the wings of the butterfly, there are 2 points which can be stable if one of the parameters in the Lorentz system is lying in this region. All right. So depending on where you start, you can go, so here is the space of initial conditions. If I started over here, I will go to the chaotic attractor. If I start in the yellow region over here, I go to one stable fixed point. If I start in the blue region over here, the green region over here, I go to the other fixed point. And so the entire space is made up into regions which go to one attractor or to the other attractor or to the third attractor, because here there are 3 attractors. All the parts of phase space that go to an attractor, it's called the basin of its attractor. And the basins of attractors can be extremely interesting. People have made a lifetime studying them. What is the shape of these attractors? So here you see that the basins of the attractors are really pretty and smooth. People can even calculate why they are the shape that they are. And you can see that the boundary between the attractor for the chaotic attractor, the basin of the chaotic attractor, and the boundary of the region that goes to a periodic attractor is nice and smooth. It doesn't always have to be smooth, right? You can have really here are some 5 or 6 different attractors, and there's one red one. All this is the basin of the red attractor. There's the basin of the blue attractor. There's the basin of the yellow attractor, and so on and so forth. It can even be extremely complicated, but I'm not going to get into that. Okay. I want to come to this idea of chance that these attractors are leading us to, all right? Now, supposing there are 2 attractors, all right, and you've got the basin of attractor A and the basin of attractor B, right? If the points that lead to attractor A are such that every neighborhood arbitrarily close by, there's a point that will lead to B, then you say that attractor A is riddled with respect to B. On the other hand, if A is riddled with respect to B and B is riddled with respect to A, then these 2 attractors are said to be intermingled. And the initial conditions that lead to one attractor or to the other are just completely intermeshed one inside the other, and it's impossible to be able to separate going to one attractor to another. So shown on the left over here is some system. It doesn't even, I want to convey the idea. All the black points lead to one attractor, all the white points lead to another attractor. And you can see the black and the white are completely meshed in very close to one another. If I take a small region of this and I blow it up, it looks exactly the same. It's fractal in its construction. And here also, any initial condition of black is very close to that of white. And if I take a region over here and blow it up, it's going to look the same, and so on and so forth. Now, this says that I cannot be very precise in choosing where to go, because arbitrarily close by to where I have chosen my initial spot is a spot that leads to another attractor. And this is what we call final state sensitivity. Let me just not spend time on that, all right? Now, so far I've tried to introduce a bunch of ideas to you, or reintroduce you to some of these ideas. There are distinct final states, we call them attractors. If the system is nonlinear, these attractors could have interesting basins. And these interesting basins may be either smoothly meshed with one another, or they may be intermeshed with one another in a somewhat complicated way. If they are in a complicated way, this is you cannot predict where you're going to start. Now, this provides for us a very natural way in which chance or acts of chance arise, even though the system may have very nice, smooth, deterministic, simple equations that are describing it. We use the coin for the game of chance. So let's go back to the tossed coin. And in addition to tossing it and giving it spin, we allow it to be imperfect, because that's what our world is like, and we let it bounce on the floor. Okay, so by imperfect, we make it, have embossing on one side, which says heads, which allows air resistance, etc. And then we have tails, which maybe have a different air resistance. And then we allow it to bounce on a non-smooth floor. And then when you do the physics, which is what these people have done in the year 2008, there you find that the basins of attraction of heads and tails get quite complicated. All right, I'm not going to discuss this paper. You all can read it later on. But what these people show is that if you adjust very, very carefully, you can go to heads or tails. Okay, but arbitrarily close to that point, there will be another initial condition that will lead you to the opposite conclusion, and therefore any uncertainty in the initial conditions can lead to an uncertainty as a result of a tossing. And this is why a coin toss, if thrown up with enough velocity and with enough angular momentum, if you do that, then it can be an approximately, even here one has got to hedge one's bets, that is an approximately random process. All right. So the physical basis of chance really is that there are coexisting attractors with intermingled basins of attraction. And depending on one's system or nonlinear system, one can have these attractors. The basins can have very complicated structure. And as a matter of fact, if they are intermingled, then it stands to reason. I'm sorry, I just had to switch on my charger. Right. Then if you have these coexisting attractors with intermingled basins, then you have the possibility that you'll have almost random outcomes. Okay. Now, whether the Necker cube or perception or whatever is governed by some sort of simple nonlinear equations, etc., that's very far from my interest. I was just bringing it as an example of how it may be of interest or relevance to the community at NBRC. But it is generally true that chance and contingency have played a very fundamental role in the natural sciences. Whether, these very singular events that have happened, we know that they have happened, the origin of life, the evolution of eukaryotes, the way in which evolution has moved, and the way in which your coin, when it bounces on the floor, that also changes the outcomes. These all have contributed, and they are very important in our in the natural world that we try to describe. And it sort of brings to fore the importance of studying complexity. Many systems are complex, and they allow a variety of possible dynamical states. And in such systems, the fact that small changes of initial conditions can lead to very large changes in outcomes. This gives rise to very complex patterns in space and time. And by exploiting such complexity, systems like us can explore new behavior and respond to the environment in new and interesting ways. And with that, let me thank you for your attention.
Thanks, Professor Ramaswamy, for an excellent talk and enlightening us on the topic. Now the forum is open for question and answers. So Dr. Arpan Banerjee, who is my colleague, will moderate this question and answer session. Thank you.
Thank you, Bhavani, and thank you, Professor Ramaswamy, for giving a very insightful talk. And I think the conceptual sort of, clarity in which you presented is always, I really appreciate in your talks. So I think we have got one question that I think came up during the chat box. So I'm going to slightly rephrase the question, which actually came. It's an interesting question. It says that can brain dynamics be captured by chaotic attractors? And if so, what are the possible physiological insights that one can make from that? The second question is maybe I think the person is kind of trying to force you to come to biology, but maybe the first question, maybe you can answer first and then come to the second.
Yeah, you see, there have been many attempts to look at chaos in the brain and to have attractors that somehow describe neuronal activity in the brain and so on, right? Precise models I'm not aware of, and Arpan may be better placed to talk about it. But the idea that the brain could have a non-trivial attractor when it is operating in a healthy state has been around for a long time. Mostly because we do need to do, the brain dynamics is very important for almost any function. And therefore, to have a very periodic brain activity is unhealthy. To have no brain activity, of course, is even less healthy. So how does one put it? It's very likely that there is huge nonlinearity in brain dynamics. Whether it leads to simple attractors or not is not very clear. All right, brain dynamics is not likely to be described by few equations. There's a lot of mathematics that goes into the study of attractors, but very briefly, let me tell you that the dimension, the Lorentz system, for example, is described by 3 equations. So the attractor is at best 3-dimensional. In fact, this is got an even lower dimension. This attractor is almost 2-dimensional. It's very flat, if you can see how it goes. All right. So if you have a 2-dimensional attractor, you can describe it by 3 equations. Now, whether or not you have low-dimensional attractors in the brain, I don't think that there is any evidence that there are low-dimensional attractors. So describing brain dynamics by few equations may not be possible. All right. I've wandered around an answer to your question, but Arpan, you want to crystallize it and bring it back to some point, or is that okay, you think?
No, I think it is okay. The first part is fine. I think if you can let the person who's asking about any physiological insight, maybe biological insight that may be drawn from that in terms of what are the underlying complexities in the system. I think that's what she's referring to. So,
okay. See, one of the difficulties in is an inference. You can distinguish between certain kinds of very extreme states. Very periodic brain activity is a certain kind of dysfunction, and so on. But to infer other states of cognition from the brain activity may not be the wisest inferences to try to make, mostly because of issues of, I don't know, ethics or what have you, because sometimes these things are tied into diagnosis. So let me not say that this is a characteristic brain signal of a person with this kind of cognitive impairment or whatever, which is perhaps what is underlying that question.
Yeah, right. So I mean, I just wanted to make a comment that, in perfectly fine synchronized oscillatory activity is what you see in epilepsy. So if you have complete oscillatory state like a perfect attractor, then it might be an epileptic brain, which is certainly not which you wish for, right? So I mean, brain certainly, yeah. So operates in certain states of fractured synchrony, and I think that's where I think these concepts of attractors come in. So let's move on to the next question, which is, I think, relates to some of these experiments by a psychologist called Benjamin Libet back in the 1980s about this notion of free will, where he kind of, are you familiar, Ram, with this concept, these experiments, these free will experiments?
I'm not familiar with the experiments.
Okay, but anyway, so just to give you a brief idea that there are some signatures of free will people tend to claim from looking at when you make a decision. For example, you can see brain activity before you actually make some decision of motor planning in terms of EEG potential. People notice that and they related it to free will. And the question, I think, kind of relates to that. So do chaotic attractors kind of relates to this notion of free will? Or if the decision making, can you say something about decision making from this? Like whether decision making is random or not, or it can be controlled by something which we think is random, maybe actually a chaotic attractor. I think that's what the person means.
Well, I mean, I'm also trying to suggest precisely that that frequently there are, okay, if I may just for a moment, gather my thoughts and explain what I mean over here. Supposing the choice was to make decision A or decision B. Given a certain amount of sensory inputs, a person may be led to decision A, and with small changes or with small additional information or with small noise, you may be led to decision B. This kind of, the state space, if one can try to imagine it, of leading to one or the other decision, could be very, very far from one another, in which case, there is, quote unquote, no choice. You will have to do this or that, right? But on the other hand, if the state spaces are intermingled in the way in which I discussed how these attractor basins are intermingled, then a small change of either information or noise or lack of information or what have you, you could switch very easily from decision A to decision B, right? So, I'm not a great believer in free will, as it happens, but that's that's neither here nor there. I suspect that one could interpret the experiments that you are alluding to in terms of at least at some gross level attractors and their basins, and the fact that they may not be very, very close to one another.
Okay, so I think I have a question and I wanted to ask you, is this initial conditions, the sensitivity to initial conditions, you touched upon it for most of the time of your talk. I think it was very nicely explained. But one thing that we see in the biological system is this issue of flexibility or adaptability. So the way that you pose the problem, it seems it is kind of preordained in some sense. I mean, what is the scope of adaptability, or how do you include that? Because that's something certainly that we see brain does over like a period of few trials. Like we are now, I mean, initially, for example, we are not very used to webinars, and now we seem to be very used to webinars and things like that. That happened very much after the first, let's say, webinar you gave. So those kind of adaptability, what's the scope of fitting that into the models that you described?
See, the adaptability, one of the things is that you don't have a single model. The model itself is evolving. So my personal suspicion is that, what the biological system does in a way is to modify its functional space. The equations themselves, so to speak, keep changing. May not be changing in form as much, and maybe some of the parameters are evolving and so on. So, I have a feeling that unless we understand evolving systems, you cannot describe, a truly biological situation, because that the biological situation, it carves out its own niche as well. If it was, you take the pendulum, for example, and if you wanted it always to operate in a particular way, then it is as if, as it operated, it would change the parameters of the pendulum to come down to where it wanted to be. That's sort of this is an individualistic Gaia hypothesis.
Right. So, to crystallize what you were saying, like maybe the coupling and all these parameters can change based on the physiology, and that's how you would imbibe adaptability in that.
Yeah,
okay.
Exactly.
So, okay. So, I think one question there was, relating to the predictability and the prediction aspects in your talk, like, what besides the person is asking that, like, let's say, for example, you showed that the clouds cannot be predicted, cloud dynamics, but the eclipse can be predicted. Is there a way to kind of determine which cannot be predicted or degree of predictability? How do you quantify that?
Yeah, no, absolutely. At least mathematically speaking, we do have a handle on that. It's what is called if you know the system, you can associate with the system a so-called Lyapunov exponent, which tells you how far, how fast initial conditions move away from one another. So the faster they move from one another, the more chaotic the system is and the less you can predict. So there is a sense in which you understand whether things are more chaotic or less chaotic, more predictable or less predictable.
Okay, so I think maybe we can have one last question, and that sort of talks about they are asking you to elaborate this phenomena, these emergent properties of the complex system a little bit more maybe in a brain science sort of perspective.
My problem is that I know so little about the context. Okay, let me just say that, look, what I think I'm advocating is the use of nonlinear models that are out of equilibrium, models that are statistical, and recognize the difficulties of these systems rather than simplifying it to a level where it's not really accurate. Right? This is not a straw man argument. I'm not claiming that this is what is done. All right. I'm just saying that there is a crying need for us to treat a complex system with the level of complexity that it deserves to be studied and analyzed by. If even the smallest amount of nonlinearity in the description tends to make systems unpredictable, chaotic, it makes them, there could be lots of very interesting new kinds of behaviors. But in coming up with models that are applicable to the brain or to any other higher level functions, the need, forget about the plea, the need is that we must recognize that nonlinearity is essential, and it can play an extremely important role in seeing what the outcomes are.
Okay, thank you, Professor Ramaswamy. I think I will hand it over to Professor Mandal. to say some final words.
Okay, so I must thank Dr. Arpan for conducting so nicely. And we have a fantastic, fabulous speaker, Professor Ramaswamy. And we had so many interesting questions was coming through. I would like to say the quote I made it is appropriate. And and Dr. Sahu, who took a lot of efforts, and also our colleague, Dr. Professor Seth, Anirban, and they all put their efforts to make this function actually successful. And thank you very much, sir. Really thank you. And
Been a pleasure. Been a pleasure. Thank you very much. Thank you all at BRC. Till next time.
Yes,
Yeah, hope to see you physically soon. Yeah.
We'll bring you physically.
Right.
Yes. Yes. Thank you. Thank you.
I'm going away from GoTo.